Any questions? Any comments? I'll continue. So let me introduce something called spin and orbit coupling. So let's think about what we have. Like, let's consider the simplest system we can think, and the simplest system is like hydrogen atom. We have like some orbit. In the center we have proton, and in the orbit we have electron rotating, right? And from the perspective of the electron, right? From the perspective of electron, you have the electron in the center, and proton is rotating, right? If you were the electron, right, you wouldn't know if you were rotating around or if the proton, right? That's why Copernican revolution took so long. So this is exactly the same system. So this is proton rest frame. And this is electrons rest frame. But in this picture, proton is charged with like a plus charge, and if a charge is rotating in a loop, it's going to give rise to currents, and if there is like a current, there is going to be a magnetic field, right? And if there is like a magnetic field, and we know the electron has like an intrinsic angular momentum, which means there will be a corresponding magnetic moment. The magnetic moment of this electron is going to couple to this created effective magnetic field. Let me call this B effective. And we want to describe this process, but like you may have figured, the way we relate objects is generally to angular momentum, because we know how to work with angular momentum. So we want to relate this B effective to angular momentum of electron in some way. So let's try to do that. So let's relate B effective to angular momentum of electron, which is L. Maybe I ask you, what is the magnetic field generated by a current loop? Does anybody remember? So B, let me forget the vectors for just one moment and just write, it is like mu0, this is not the magnetic moment, this is vacuum permeability, right? It's from the electromagnetism, and there's like a current, and you divide this current by 2R. So if you don't remember, that's fine, you can just open your textbook and remember, but that's the result. But the current I is equal to, in this case, plus E, because it's the proton circling, divided by T. And T is 2 pi R over V, so let me write that. So this is E over 2 pi R divided by V, but V, I'll put it here. So then I can just plug this in here. So then this B is going to be mu0 over 2R and this entire thing, right? But like I said, I want to derive something in terms of angular momentum, and to do that I'm going to multiply this with M, multiply this with M, I'm going to multiply this with R. So I already have R squared, let me R squared, I'm going to make it R cube. And this MVR is angular momentum. So this object is L, right? So this is L. Then this thing is going to be equal to nu 0 E divided by 4 pi. I have 4 pi r cube m times L. And to make it a vector, I'm just going to put B is a vector and L is a vector. Okay? Any questions? Simple stuff. Like I'm just using what I know already. Then, okay, then this B is going to couple to spin, right? Then there will be like some U is equal to, if you remember it was like minus mu, now this is angular momentum due to spin S, dotted onto B, and this is B effective, and this is going to be minus, there are like two nu zeros, but one is permeability, the other one is magnetic moment, but magnetic moment is related to L, right? From here, if you want, there will be proportionality constant, but let's not worry about that. It is going to be of the form L dot S. Okay, some constant times L dot S. Yes?
For current, you multiply by V, right?
For current, I multiplied?
By V.
No, so current is charge divided by time, but time is total periods, which is 2 pi r, divided by velocity v. So that's why it was actually initially here, I just put it in the numerator. So let's estimate how strong this effect could be. Okay, like a couple of observations. So no L, if L is equal to 0, coupling is 0. So spin orbit coupling is a coupling between orbit and spin. You have to be a non-zero, you have to have like a non-zero spin and also a non-zero angular momentum. For example, this doesn't happen for S orbits.
You said not equal to 0.
So if, yes, if L is, yes, thank you. If L is 0, coupling is 0. Yes, thank you. Good. And now let's estimate how strong this effect should be. Let's estimate. So I'll do two estimations. I'm going to estimate the strength of the magnetic fields, and I'm going to estimate the energy. Let's estimate the B first. So B is this, right? Let's write this. So this is B, approximately order of this. For L, I'm going to put H bar L plus 1. So for, there is like R0, for R0 I am going to put like R is approximately N squared A naught. Maybe I can remind you how to get this in a little bit, but let's for the moment focus on this. And this is going to be A naught cube, and there's maybe like some power of N. For simplicity, let's take N is equal to 2 and L is equal to 1 state, right? This is one, it is like 2p state, so this is 2p state of hydrogen. Now, as you can see, mu 0 is a fundamental constant. It's like 4 pi times 10 to minus 7. Electron charge 1.6 times 10 to minus 19 coulombs, something like that. H bar is a constant. A naught is like something like 0.5 angstrom, right? We calculated that before. Pi is pi, m is electron mass, and n is going to be 2 for this. So all the numbers I know, L is equal to 1. I can just write them and calculate the result. And what I found here is B effective was approximately 0.5 Tesla. Yes?
U is proportional to L, and the delta B is related with angular momentum.
U is proportional to L, yes. And
What is proportional with spin?
it is both proportional, it is proportional to inner product of L and S. I have an angular momentum for L, I have another angular momentum for S. I take their inner product and that's the proportionality. So this is, if you want, is equal to some constant times L dot S. Is there a problem? That's good? Okay.
How did you think about N2 A naught? Because
So this maybe I can drive in a little bit. So
no, I'm not asking that. You inserted that into the equation and you just wrote N.
so this is the equation I derived earlier, right? Do you have any problem with this?
No.
So I just copied this, and here I have to substitute two things. First is the angular momentum, and for angular momentum I use what I know. It is the magnitude is h bar L plus 1, and there's also a radius here, and for the radius I substitute the radius of 2p orbital. N is equal to 2, and A naught is Bohr radius, which is 0.5 angstrom. So that's A cube, and there's also I think some n to the n squared times cube, n to the 6, something like that. There's like overall constants. Yes, good. So the result is like I found effectively a magnetic field of order 0.5 Tesla. And my question to you, is this big or small? Huh? Big? Yes. How big is it?
If I remember correctly, Earth's magnetic field is 0.5 Tesla.
No, Earth's magnetic field is much smaller than that, right? Like, for example, the bar magnet you use in your refrigerator is going to be like millitesla. It's like 0.01 Gauss or something like that. When you come to order of Tesla, that's like giant, right? To get this kind of magnetic field, you have to get into MRI. So that's huge. So this is not a small effect. But luckily, we don't have to worry about that because there's R cube. As long as you are far from the proton, it's going to be decreasing with 1 over R cube, which electron cannot do. So we can similarly estimate the U effective. So U, let's estimate U. And for U, B is estimated. For nu S, I'm going to put spin, right? This is going to be, mu is what? Mu is, if you remember, this is some G times E over 2M times H bar over 2, right? So that's the magnetic moment we derive many times. You multiply whatever you found here with this, and you are going to find, I think I found approximately 10 to the minus 5 electron volts. So energy spacings are order of electron volts, and you are going to have like a very fine splitting from that known result. And that's why this is called fine structure. Okay? Any questions or comments? So maybe I can do the following. So I have originally I have this 1s, and I have this this is 1s, and I have this 2p, and I can just make a transition from 2p to 1s because all selection rules are obeyed, and I am expecting, like in the spectral domain, I'm expecting just a single line, something like that. Maybe. But once I consider this spin orbit coupling, the same picture is going to be modified just a little bit. What is going to happen is this 2p is going to, right, because of this nu dot b, I am going to have something of order nu Bohr times b effective for one spin, and mu Bohr minus mu Bohr times mu effective for the other spin. So this entire splitting is going to be 2 nu Bohr times b. I'm going to divide this single line to two lines. As a result, the transition will be either this line or this line, and initially this line is going to be missing, but rather than I'm going to have two lines. And this is going to be like a tiny order of 0.1 nanometer splitting from the original line you observed. Okay? Any questions or comments? So for these kind of estimations, I notice people are having problem, like for example, to estimate this. Maybe we can quickly, suppose we are desperate and you forgot this relation. Let's estimate this Bohr radius, for example. Let's estimate how to find these things. I think, reminder. You don't have to go and do de Broglie every time. So there's like a quick way to do this. And at least the one I use is like something like this. The energy in the state, like suppose we are considering one as state, is going to be h bar squared over 2m a naught, right? And so this is the total energy. How do I know this? If you remember the Schrödinger equation, h bar squared over 2m d squared over dx squared psi, I have to have something of unit of x here, so that it is going to be on the other side e times psi. And the only reasonable thing is to use this Bohr radius a naught square, right? I fix my mistake now. And there's like a minus. And the second thing I'm going to use is in the Coulomb field, the total energy is half the total electrostatic energy. So the total electrostatic energy is minus 1 over 4 pi epsilon naught E squared over R. So this is my energy, and half of this is my total, right? How do I find this? I find this from the equilibrium between centripetal force and gravitational force. Okay? And for R, I'm going to put A naught. And if you modify this equation, let's play with this and then find A naught. So cancel this with this. This 2 is going to cancel this 2. Minuses are going to cancel. I'm going to have h bar squared here, and I'm going to have m here. So this 1 over a naught is this. So I found the Bohr radius. Then a general orbit, r, n, is going to be scaling with n square a naught. This I know. And I can also, for example, 13.6. Suppose you forgot that. You can substitute this a to here, and this is going to give you 13.6. Or if you remember 13.6 from here, you can use it to derive other things. Okay. Put this like a reminder. This is like a side note. Any questions or comments? Now, as you can see, there's like in my Hamiltonian previously, which was like the Schrödinger equation for like Coulomb field, I need to have an additional term. So there is like h is going to be some h plus this constant times L dot S. Okay, now we have like a term like this, and what this says is like, suppose you are the spin angular momentum, right? Suppose you are the spin angular momentum. You are going to experience a torque due to orbital angular momentum. So your spin is going to change due to orbital angular momentum. In the opposite way, suppose this is S, so this is going to be some B effective on the S. Or if you are like L angular momentum, due to, right, you can repeat the same argument for like, there will be like a torque on the L due to S. So L and S are not going to be conserved by themselves. So L and S change, and they are not conserved. Is that clear? But there's some, but we can look at the total sum, right? And we can define J is equal to L plus S is conserved, as long as there is no external magnetic field, is conserved. So we can work with total angular momentum rather than L or J. And this brings us to so-called addition of angular momentum. So let me write that. So now I have to determine, given L and S, I have to determine like L is quantized, S is quantized, and from these like constraint values, I have to find constraint values of J. That's the problem of angular momentum addition. So let's consider like a cartoon picture to see how to do that. Suppose this is my, I don't know, suppose L is something like that. Suppose this is my L. And as you remember, if this is my z-axis, there are like two orientations of L. There will be like one up, the other one is like that, but let me not write that. Suppose L is the bigger momentum, like the big brother is L, and for the small one, suppose this is my S, so this is S, and there are like two orientations. For every spin, there's a plus h bar over 2 and minus h bar over 2. The other one is going to be something like that, right? So, okay, this thing I know J is like we said angular momentum is right angular momentum. Once you find the rules, they are unchanged. Whether you use J or L or S, it's the same thing. And from here I know, first of all, sum of J is supposed to be H bar, some J plus 1. Right, this is the magnitude of the vector. And there will also be some Jz, which is going to be mj h bar, and this mj is going to be minus j dot 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 to j. And to find the allowed values of j, then I can consider the maximum possible j and minimum possible j, right? The maximum possible j is going to be like this. I'm going to use these projections, and I'm going to find the maximum possible projection I can build from these vectors, and I'm going to find the minimum possible projections from these vectors, right? So maybe I can do that, and you can see what I'm going to do. So what I can do is I can, for example, take this one, right? This is going to have some projection, some LZ, and to get the maximum, I have two options. I'm going to get this guy. Oops. Yeah. So this guy. So this is L, this is S. So this is LZ, this is SZ, but the maximum value of LZ is what? What is the maximum possible LZ? L, right? It is the maximum possible L. What is the maximum possible SC? If you want, there's H bar, but I'm not going to write H bar. It's the same way, right? This is S, H bar. Then the maximum possible J max, is going to be equal to L plus S. Good. And similarly, I have to like find the minimum possible one. For the minimum possible one, I'm going to just take this guy. And now it is not going to be sum of like their like projections, but difference, right? This is subtracted. So this is the total, and from the total, like from L, you need to subtract the little one to get the total. So J min is going to be, in that case, L minus S. But to make sure this is like positive, we sometimes put this like this. Then addition rule is addition rule. So J can be anything from L minus S all the way up to L plus. Since they are both positive, I don't need absolute value. And now, of course, J has to be an integer. And for any given J, we are going to have Mj is equal to minus J dot 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 to J. In total, 2J plus 1 possibilities. Good? Yes?
The maximum value for L and S happen when the vectors are in the direction of Z, right?
Like, yeah, this is a little bit confusing because when we write like this, right, we emphasize, like we made like a big story, right? You cannot draw angular momentum like this. So what we should be thinking is like there's actually some angular momentum precessing around z, and that's the projection. Is that what you're asking? Yes. So there's like some L. You don't know the direction, but it's like precessing like a spinning top. There's another thing that's precessing like a spinning top. And I look at these two things and I said, what is the maximum thing I can build from these two things? Is that what you asked, or did I ask?
Maximum comes from the projection.
Yes. And the reason is because like this rule, right? Mj for any given L, ML is going to be from minus L to L. So the projection, whenever the projection is maximum, I have the angular momentum number. That is what I use to get these rules here. Is that clear? It is hard to say too many words, but simple to think, right? How can you build, you have these two vectors, how can you maximize and minimize them?
Okay. What happens if it's not maximum? Do we have that case?
All the cases are here. There is no other case, right? Yeah, quantum angular momentum is quantized, and when you add them, you have to add them with the quantization obeyed. So that's what we are trying to do here. So the picture now is like, okay, this is also cartoon, but I think it helps us to see or understand what is happening. Okay, suppose this is my z direction, and I want to like have this, I have to have two angular momentums, like one is L, suppose this is my L, like something like that. This is my L. And I have to have another one for S, suppose this is my S, I don't know. Something like that. So this is my S. And what we are saying is like each one is like spinning like this. For example, this one is like precessing around some z axis. Oh, sorry. I take it back. So this is without magnetic fields. So let me take that and write for myself to remember. So this is B, and if there is no B, I need to have a direction, and the direction here is like determined by this dashed line, which is the direction of JZ. So this is JZ direction, right? Of course, I cannot write it, but like I can imagine it to be this way. And L is precessing around JZ, and S is precessing around JZ. This is the picture. So I think I have something like that. Yeah. So this is my L, and this is my S. Okay. Now, if I have a magnetic field with B, so I'm going to have like a preferred direction. Maybe I can use something like this. Maybe this is my B direction. So this is BZ. And I have to take this entire picture, and this entire thing needs to precess around this. Like I put it here first, and I'm going to make it precess. Something like that. Right? Now, my JZ line is going to precess like that. Something like that. So this is the fine structure. I think we may or may not think about this, but let me just list a couple of things. So you can see we start with like a very plain, only n-dependent energy spectrum, but now this energy spectrum started to split into sublines. And every time you take like a Neve effect, this is going to be the case. And you are going to get like more and more and more fine structure as you consider this. For example, we can consider relativistic correction. In the Schrödinger equation, we didn't solve a relativistic Schrödinger equation, right? We solved it for non-relativistic case. And to get the relativistic correction, you can just use this p square c square plus m square c to the 4 is approximately the first power is going to be mc squared, the rest energy. The second one is going to be p squared over 2m, right? And if you do the Taylor expansion, there will be another one which is like p to the 4th. And you can just put this in, and that's going to split your energy eigenvalues. So this is one contribution. Another contribution is so-called hyper. So this was the fine structure. We can also consider hyperfine structure. Just like electron, the nucleus also has a magnetic moment, right? It is also a quantum object. It also has angular momentum, and if it has angular momentum, it has a magnetic moment. So proton, for example, or let me call it nuclear magnetic moment, something like, let me call it mu n. And if this is like a magnetic moment, non-zero, right? It is like a magnet, and a magnet is going to influence other magnets. They want to be aligned, and if they are anti-aligned, there will be like energy punishment. As a result, there will be, for example, this mu n dot total J coupling on our electron. So this is going to split lines even further. It's going to be hyperfine structure. And on and on. For example, there's one more. There's so-called, since we talked about this last time, let me mention one more thing, so-called lamp shift. So in the solution, we, for example, take like a plain Coulomb interaction, E squared over R. But we last time talked about so-called vacuum fluctuations of electromagnetic field, right? The electromagnetic field just comes out of nowhere. There's nothing you can do about that. Then this vacuum fluctuation, so vacuum fluctuation, also modify some levels. And each time, each problem comes with like a new term you add to Hamiltonian, and you play with it, and you find the modification of the spectrum. So the lamp shift is like, so what we said is like there's like a proton, right? There's like a proton, and there's like electrons. Suppose we are thinking about hydrogen atom, simplest thing. And we found everything. But what we said is like there's also so-called vacuum fluctuations. Like there's like electromagnetic field coming out of nowhere, right? Two photons just emerge from nowhere, and then they disappear in a split second, like something like delta E, delta T bigger than h bar over 2. But if there's like an electromagnetic field, right, this is E and B field, an electron is charged, so it is going to couple the electron, and it's going to modify its behavior. But the way we describe this is like there's like some spectrum, and this spectrum is going to modify due to this lamp shift. This is even tinier than lamp shift. For example, fine structure is like what? 10 to minus 5 electron volts. Hyperfine structure is even smaller than that. I think 10 times smaller than that. Lamp shift is even smaller than that. But the key is, can you observe it? And of course, it is observed. That's why we are talking about this. Okay. So if we add, like, for a single electron, we can add different components of angular momentum. Similarly, we can also add angular momentum of different electrons, right? Suppose we have like a many electron system. So they are like, let's suppose these are electrons, I don't know, like something like that. And each one has like some spin S. Maybe they are bound to some nucleus. They may also have L. Maybe they have J. This one also has like some S. Maybe some L and S. Another one here, another one there, another one here, right? So the addition rules are exactly the same. So I can just form two vectors. I first, of course, there is no one way to do this, but generally we first sum all orbital angular momentums. So for example, L, total. Sometimes I total, but let me not clutter it for the moment. Sum over all particles, Li. And similarly, S, I can write T, but let me not write it. It's going to be sum over all Si. Good? And the rules are again the same. So this is going to be, for example, Lz is going to be ML H bar. Let me push that just a little bit. Maybe here. And this ML is going to be minus L dot 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 to L. Similarly, there will be some total SZ, which is, let me use uppercase here. This is uppercase MS H bar, and this MS is going to be minus S dot dot S. And to sum the total angular momentum, I just form this J. If you want, this is like a different J, like some calligraphic J, which your book does it, but I cannot do it when I write, so I'm just going to use the same J. It's going to be total L plus total S, right? There are many terms inside, and I add all of them. And here, this J again, this L has the magnitude. Okay, magnitude of L is H bar L plus 1. Here, magnitude of S is H bar S plus 1. Then magnitude of J is going to be H bar J plus 1. And Mj is going to be minus J dot 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 to plus J. And like typically, okay, now you can think about what exactly this picture, right? This picture adding two things, and if total L is bigger than S, you can do what I did for L, exactly the same thing. If total S is bigger than L, you can just take one orientation of S, and you can consider two orientations of L. Whichever is the bigger brother, you start counting from that. And for this, okay, if L is bigger than S, we are going to have J has 2 S plus 1 values. And if S is bigger than L, then J has 2 L plus 1 values. Okay? Suppose we have 2 electrons, and suppose one is has like L is equal to 1, the other one is L1 is equal to 1, L2 is equal to 2. Now I'm going to first add and find total L, which is going to be L1 plus L2. And here L, the magnitude of this L, can be the difference, right? L2 minus, let me write first, L2 minus L1, absolute value, all the way up to L2 plus L1. And that means it is going to be 1, 2, and 3.
How it will be
From here, right? Like the difference, minimum possible is the difference. 2 minus 1 is 1. Maximum possible value is 3, and I have to go in integer steps. Of course, like you have to have like a certain orientation of L to get that, right? You have to bend them a little bit so that you get that. But the rule is like this. All the possibilities are in between. Similarly, okay, let's do exactly the same thing. S is going to be equal to S1 plus S2. And the magnitude of S is going to be S1 minus S2 all the way up to S1 plus S2, but S1 minus S2 is 0, and S1 plus S2 is 1, and there will be only two possibilities, 0 or 1. Typically, like this is sometimes called singlet, this is sometimes called triplet, but let's not get into that. You'll learn it in more detail in another course. Now I added L and I added S. Now let's add J. J is equal to L. Without any index, this is total plus S. Now each one I have to add one by one. Now the possibility 1, L is equal to 1, then I can have J is equal to, okay, let's tabulate it. So it's going to be L is equal to 1 and S is equal to 0. L is equal to 1, S is equal to 1. L is equal to 2, S is equal to 0. And L is equal to 2, S is equal to 1. L is equal to 3, S is equal to 0. And L is equal to 3, S is equal to 1. All the possibilities are considered. And for this one, for example, let me just write and at least take one so that you can do the others if you are interested. For this one, I can have L minus S dot 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 to L plus S values. I don't need this here. And it is going to give me L minus S is 1 and L plus S is 1. There will be only one possibility. This one, L minus S is again the same thing. L minus S is 0, L plus S is 2, so it's going to be 0, 1, and 2. This one is, again, only 2. This one can be what? 1, 2, and 3, and so on. It looks a little bit elaborate, but it is not. You just need to consider the possibilities one by one. So in total, J can be, for example, 0, 1, 2, 3. I somehow found, okay, this one is going to give 4, right? This one, 3 minus 1 is 2, 3 plus 1 is 4, 2, 3, 4. All the way up to, so total J can be 0, 1, 2, 3, and 4. So I think last time you asked, is there like a particle with total spin 4? So not a fundamental particle, but a composite. If you put like a 2 electron in a bag, they may have like 4 angular momentum. So, okay, one last thing and let's take a break. So these systems are called composite systems. Composite. This means there are some of smaller fundamental units, and now the composite itself, like, okay, like I have like a bag. Inside the bag I have like a bunch of things clustered together. They could be electrons, they could be protons, neutrons, all kind of mass can be inside. But whatever it is, I can add the total angular momentum. And after adding total angular momentum, J can be either integer or half integer. Right? For example, here we added 2 half integer objects, right? 2 electrons, 2 half integer objects formed an integer angular momentum object. If we had like an integer object and a half integer object, the sum would be a half integer object. So then the total can be integer or half integer. If the total is integer, we are going to call them bosons. Exactly like fundamental particles, we don't care about internal structure anymore. This bag itself is either a boson or fermion. If J is integer, it is boson, and they are going to like obey Bose-Einstein statistics. If total J is half integer, it's going to be fermion. And if they are fermions, for example, they are going to exclude each other. For example, 2 atoms, if they have total angular momentum in half integer, you cannot put them together. Okay, let's take a break and continue in the second hour.